in a lot of publicly funded programs, you have the big risk of sunk cost argument. We spent £30 million on this, we have to proceed. Now, we never got into any of that sort of thinking. Some of our very early shareholders said, never take a decision to push on if the evidence doesn't support it. And so we cut a few things, learnt fast, forced ourselves to do things with relatively modest resources.
Welcome to the Lab to Market Leadership Podcast. Too many advanced science and engineering companies fail to deliver their innovations from the lab to the market. We are on a mission to change that. My name is Chris Reichhelm, and I'm the founder and CEO of Deep Tech Leaders. Each week, we speak with some of the world's leading entrepreneurs, investors, corporates, and policymakers about what it takes to succeed on the lab to market journey. Join us. Deep tech is often associated with moonshot technology programs, and fewer programs can be considered more moonshot than nuclear fusion. For years, it's always been one of those things that's 30 years away. But is it still? With all of the development and all of the technology and all of the investment happening into fusion, are we getting closer? To help me answer this, I'm joined by Dr. David Kingham, the founder and original CEO of a company called Tokamak Energy. Tokamak could be one of the companies that helps us realize the benefits of nuclear fusion by the development of something called a spherical tokamak. If you don't know what that is, that's okay. I promise you'll find out. With David today, I want to get into their lab to market journey. I want to understand the types of milestones that have guided them from science project to something more resembling a business. I want to understand the skills, the experience, and the talents required to do really big things at the scale of a new form of energy generation. This is going to be a great show. I hope you enjoy it. Let's get into it. David Kingham, thank you so much for joining me.
Thanks, Chris. It's a pleasure to be with you today.
As a founder and as a chief executive, the first chief executive of Tokamak Energy, I am thrilled to have you on the show and to learn more about the evolution of what has become, I think, and it's no exaggeration to say this, one of the leading nuclear fusion companies in the world today, promoting the spherical tokamak design. And it would be great to understand the lab to market journey that Tokamak has been on. And so as you've been around for this journey, I feel very fortunate to have you. Take us back, if you would, to the beginning. And,
Sure.
Where did all of this start?
Yes, it's been quite a long journey so far, and there's a few more miles to go. So 15 years ago, I teamed up with two scientists from the UK Government Research Laboratory working on fusion. And it would be fair to say they were frustrated by the slow progress, particularly of very large government fusion programs. And now these two guys, Alan Sykes and Mikhail Grzhinovich, had fantastic success in the 1990s with a small spherical tokamak. It had achieved record results and was recognized by US and UK government as being a very promising route to commercial fusion energy. But it was kind of lost in the noise behind the excitement of the jet tokamak at Culham, which achieved 16 megawatts of fusion power. So there was this little high-performance device and a fantastic big 16 megawatt fusion reactor. And then the whole world decided that scaling up the jet tokamak, the one that achieved its 16 megawatts, scaling that up was the right way to go. And, we didn't all think that. Some of us thought there had to be an alternative way to go, which might be faster and more commercially relevant.
Mm. And in those early days, was it just the three of you, or were you starting to pull together the early foundation for a team beyond just the founders?
Really, just the three of us, to a few helpers at the very early stage, and then some investors started to come in. We were very fortunate with early investors. We had what is now the UK Science and Innovation Seed Fund, that's designed to help spin out technologies from government labs. We had an investment from Oxford Instruments, superconducting magnet business, and from Sir Martin and Audrey Wood, who were the founders of Oxford Instruments, who really had a passion for getting small businesses started. So they were very much part of the team early on.
And was the focus about developing or scaling up that tokamak?
The initial focus was, initially we thought fusion energy is too much for us to attempt, and we should look at the spherical tokamak as a scientific instrument with high performance plasmas, and basically wait until someone else comes up with some other innovation. And we had an internal debate at the time around high temperature superconductors. And our chief scientist, Mikhail Greznovich, was saying, this has to happen. We need this new material. And I kept saying, well, that's fine, but it's not manufactured as a usable engineering material yet. And but he was right. We had to have it, and I was right at the time. It wasn't ready.
Yeah.
But 2011, a guy at Oxford Instruments told us that they'd had a new batch of high temperature superconductor from a company called Superpower in the US, and that it was ready to use to make magnets. It was good enough. So we thought, well, we better try it. So at that stage, Mikhail phoned up his friends in Prague and said, can I borrow your tokamak for the summer to do an experiment? And I mean, tokamaks are not very common devices, so this is quite a big ask. So they said, well, you can borrow it for 2 weeks. At which stage we thought, can you really put a magnet on a tokamak in 2 weeks? The answer is yes, you can, so long as you've got everything prepared beforehand. So this was, it was a very Heath Robinson sort of experiment involving a cryostat made of plywood, some aluminium foil so that it didn't leak, and you could pour liquid nitrogen in, and then a coil was wound out of 25 meters of this superconductor. And we worked out how to connect a power supply to the superconductor, and it all sort of boiled and fizzed. But it worked. It worked. We could produce a significant magnetic field with very rudimentary setup and engineering, and the tokamak worked. So, so then we went to investors who were interested and said, actually, this new material does the job we hoped. And we can see how to make more powerful magnets using this material. And it gives us a route to commercial fusion energy. And then we worked out all the other things we'd need to do on that journey.
So that actually, so getting to that milestone, if you will. So
Yeah.
experimenting with this new material, the Heath Robinson approach you took to kind of validate that initial approach and the material. How many people did you have in the company at that point?
3.
Okay.
3. Yeah, 3 of us at that point. Yes.
Right. And
I mean,
and
we
how
had
much
help
capital?
from
Yeah.
how much
But
capital?
you had help from others too.
Yeah.
And how much capital had you raised as well?
About $200 million. No, about $200,000.
Okay.
$200,000.
$200,000. All right.
Yep.
So $200,000 raised at that point. 3 people. And you had already come to a conclusion, hey, if we can now just continue to focus on this and build this and scale this up, we can get to a point. That seems like actually a reasonable return given the amount of money invested. And the talent that you had on board.
Yeah. And we were certainly first to really see that high temperature superconductors could be used successfully to make magnets for magnetic confinement fusion. When the material had first been discovered in 1987, lots of people were speculating that it could be useful for fusion. But then everything went quiet because manufacturing the superconductor was so difficult. It was only 2011, really, that the manufacturers had worked out how to make the material that we're now able to use.
And did Oxford Instruments continue to act as a partner or supplier to Tokamak Energy, or did you have to go off and do this yourself?
Yeah, so Oxford Instruments then worked with us for another 4 years to scale up the technology. We were both learning about the material and the technology as we went forward, but we needed their superconducting magnet expertise. And we got to 2015 when we were able to demonstrate a plasma for over 24 hours in a small tokamak constructed with high temperature superconducting magnets. And that was a big milestone for the company. And that meant we could raise about $15 million to really push things forward.
And so, David, in terms of technology readiness level at this point, by 2015, you get to that next milestone. Where would you say you were at that point?
Yeah, it's technology readiness level 2 or 3. I mean, it's
okay. So this is still
prototype.
A function of research. This is a functional. Okay. Oh, that's interesting.
Yep.
All right. So so you're still very early stage there, but you've got enough to contain plasma. Is that right? Am I understanding that correctly? To contain plasma for a period of 24 hours using materials and systems that would broadly be in place within a fully scaled tokamak.
Yep. Yeah. It's modest experiment by today's standards, but it did the job. At that point, we decided this superconducting material is fantastic material. We need to build our own team. We can't be reliant on someone else to do the development because we want to go at our pace. But by then we had enough credibility, enough people knew about us that we could recruit a really good team. And then you get this effect that we're trying to build a business based on fusion and superconducting magnets. And we're in a place, Oxford, where there's 50 years history of research in tokamaks and 60 or 70 years history of research in superconducting magnets. So you've got all this human capital in the area that makes it feasible to do really difficult things.
Yes. Some segments of the deep tech universe are associated with science projects more than businesses. And for many, nuclear fusion has been one of those. The big, the big adage with nuclear fusion was it's always 30 years away. And until now, one gets the sense. Now, hopefully, it's not another 30 years. One gets the sense we're closing in on it. At what point was 2015 the point for you guys where it shifted from kind of science project to now business?
No, I think it was still science project at that stage. If we after 2015, we were still judging success of the business and reporting to shareholders based on technical progress. There were no sort of commercial milestones. We weren't promising to sell anything to anybody. We set a series of milestones which were achieving a 3 Tesla magnet, a 5 Tesla magnet, going up to 10. I mean, Tesla is a measure of magnetic field strength. Conventional superconductors can typically get up a bit above 10 Tesla. High temperature superconductors have the promise of getting to 25 Tesla, 30 Tesla or more if you need it. And they can do that in a fusion device, which low temperature superconductors really can't do. So we had to have these goals for increasing field strength. And we also set a really big goal in fusion of getting to 100 million degree plasma temperature. Now, in retrospect,
why is that important?
So 100 million degrees is really the threshold necessary for commercial fusion energy. If you have a temperature that high, you get energetic collisions between ions, and that significantly increases the probability of fusion reactions happening. So you have to get your plasma to that sort of 100 million degree and above temperature. And it doesn't matter whether it's a tokamak, a spherical tokamak, a stellarator, or laser inertial fusion. You still have to get your plasma to 100 million degrees so you get the collisions are energetic enough so the ions combine and produce more energy.
Okay, so that's interesting. Regardless of the design then, that 100 million degrees is absolutely critical so that you create what sounds like the conditions for a fusion then to start taking place.
So we set that goal. Our next device, we will reach 100 million degrees. And very few fusion devices have actually reached that temperature. The jet tokamak in the UK, TFTR in the States, a Japanese tokamak, and more recently, the National Ignition Facility in the States have got to that sort of temperature. But nothing else has, because it's really, really difficult. So
now, if I may, let me ask a question. Early investors who are coming in to support the development of Tokamak Energy, and we've talked about how it's still, and it sounds like it had to continue being a science project in order for you to at least be able to demonstrate that the vehicle you were creating was capable of creating the conditions for the type of energy you're trying to generate. And so, but how does that work from, your perspective as a company trying to generate investment to keep yourselves going, knowing that there's no immediate prospect of commercial activity?
The 100 million degree target was really agreed with the shareholders, with the investors, as being necessary, but perhaps not sufficient to take us all the way to fusion energy, commercial fusion energy. And so they were very happy with that bold goal. And then what has happened in practice is that the business has moved from trying to do everything itself into much more of a partnership collaboration model with government and with other private companies.
Yes.
So our market position now is we know how to build tokamaks, we know how to build high temperature superconducting magnets, we know about plasma control systems and so forth. Those all work fine. So we're nicely positioned to be a partner in major government-funded projects. For example, in the UK, in Japan, milestone-driven program in the States.
Yes.
So we're looking for alliances, collaborations to take the technology forward. We're looking in some cases for governments to be the customer for that development. In other cases, to be the co-funder. So we're using shareholders' funds very efficiently.
Mm-hmm. But at the early stage then, so up until this point, I guess it's a matter of targeting the right kind of investors who see the world in a slightly different way, who I'm guessing, for lack of a better term, are just the most extraordinarily long-sighted investors who believe in the potential impact of what can be created directly and indirectly.
Sure.
Is that a fair assessment?
Yeah, I think that's exactly right, that our early investors liked the scientific argument for the spherical tokamak being very efficient, and they loved the properties, the fundamental properties of the high temperature superconductor. I mean, it's a material that delivers huge current densities, even in a strong magnetic field, even at relatively high temperatures, like 20 degrees above absolute zero. So our investors could easily see the potential, even if the business model might need to change over time to get the whole job done.
And of course, you were the CEO from the earliest days, and you mentioned 2015. You achieved another significant milestone, and that thereafter it was still a science project, but with the raising of an additional £15 million, you could move forward in a way with clear targets, even on some of those future technical milestones. At what point, David, did you feel that it was time to hand over the reins to a new CEO?
Right. So this was about 2017. Our 100 million degree target was still a bit out of reach, but we had achieved an intermediate target of 15 million degree plasma temperature, which is not insignificant achievement. It's hotter than the center of the sun. But we realized there was some serious engineering to do to really get through, and some clever physics to be done to get through to 100 million degrees. So we did several things there. It was pretty clear we needed stronger engineering leadership. I'm really a theoretical physicist by training, so it's time for me to step into more of a supporting role, get an engineering chief executive in. Then we also established a collaboration with Princeton and Oak Ridge National Labs in the States, funded by US Department of Energy, so that they could help us with some of the plasma physics that would help us get to this 100 million degrees. And we got there we announced it in 2022. Looking back on the data, we were there or thereabouts in 2021. But we
with
wanted
that 100 million degree target.
With 100 million degree target achieved and achieved. Now, it would be easy to claim and easy to not measure things perfectly. So we really wanted to be absolutely sure that the measurements were robust, repeatable, peer reviewable, backed up by colleagues at Princeton and Oak Ridge who know about measuring these plasma temperatures.
Yes.
We certainly wanted to go right at the a maximum scientific proof point end of things.
Yes. Gearing up, even getting to 15 million degrees is one thing. Getting to 100 is another thing. These are incredible engineering challenges.
Yeah.
How can you talk a little bit about how you guys approach that from a capability standpoint? Where did the talent come from? How are things organized? There are lots of our listeners who are also wrestling with huge engineering challenges and thinking about that which is required to galvanize, motivate, and at the end of the day, get the results that are required in order for you to hit the milestone. What kind of lessons did you learn from that whole experience?
The way we worked was incremental. We had incremental milestones. We had the 15 million degree and 100 million degree milestone, and the increasing magnetic field strength milestones in with the superconducting magnets. But the team evolved, and the sense of it was very different from a sort of big scale government-led program, which tends to start with the specification requirement and then recruiting a large team to deliver. So a rapid scale up of people and then progress towards the project. We were much more, we'll only recruit more people if we achieve the previous milestone, and so learn as you go on the scale up. Now, that may not be the fastest way of getting there, but it has the advantage that if something doesn't work out quite as expected, you're not overcommitted to pursuing it. So you in a lot of publicly funded programs, you have the big risk of sunk cost argument. We spent £30 million on this, we have to proceed.
Yes.
Now, we never got into any of that sort of thinking. Some of our very early shareholders said, never take a decision to push on if the evidence doesn't support it. And so we cut a few things, learnt fast, forced ourselves to do things with relatively modest resources, and the other thing we were trying to do with the magnets in particular was to achieve the highest possible field strength in the smallest possible magnet. So you're using materials as efficiently as possible, and you're not physical size scale up can come later once you're satisfied that you can handle the
once
engineering.
You get through the prototypes, successful prototypes for the thing that you are. So if I'm hearing correctly, one of the things that may be, and it's interesting, the piece around resource constraint, around not growing too quickly, but making sure that, for want of a better phrase, you've mastered the lesson that the challenge is trying to teach, if you will, and that you can represent that in a at the TRL 4.5 stage where you're developing your prototypes. Don't worry about the size of the prototype. At that stage, can you actually try to do what you're trying to do? So if I'm hearing correctly, almost stay small. Don't worry about trying to scale so fast. Stay small until you've got it. And then you can worry about the challenges associated with scaling later on.
Yeah.
Would that be a fair summary?
I think that's a fair summary. Of course, while you're doing this, you're trying to file patents on all sorts of innovations you come up with, some of which are driven by trying to do things in as compact, a small manner as possible. You're also building your supply chain relationships.
Absolutely.
Learning that in the high temperature superconducting world, there are many manufacturers of the basic material, and then very few people who know how to turn that material into powerful magnets, robust, powerful magnets. So we used quite a few different suppliers, and learnt how some manufacturers produce better tapes than others. There are different properties, different manufacturing techniques we use, different costs from various manufacturers. And here we are making lots of little magnets and learning quickly how to use everybody's material. We're also developing sophisticated modeling software. So, you build a small prototype, you measure everything you can, and then you build your numerical models, your software and simulation, so you really understand how these small magnets work. And then you can, with confidence, design a bigger magnet and a more powerful magnet. And then you test that. And if that works as intended, you get more confident in your modeling and simulation. So
how reliable are the models? Or if you are continuing to experiment at these smaller scales, how much is scale a factor in the realization of what you're ultimately trying to achieve? How much more do you have to account for scale when it's finally time to, it's always more than just a matter of, we'll just, here are scale up ratios and there you go.
Yes, sure. Because manufacturing techniques have to change as you scale up.
Sure. Yeah.
So we started off winding superconducting magnets as a spiral of tape, and circular cross section, and that's relatively easy to do, and we've got more and more efficient at that. Then you need to think of larger scale and then different shapes, because some of the coils in a tokamak have to be more or less a D shape rather than a circular shape. And that creates additional manufacturing challenges. So you're trying to work out the manufacturing challenges at the same time as developing the software and simulation so you can predict how the magnet should work. You build one, test it. Did it work as intended? If not, what's happened is our modeling software not quite right? Is the manufacturing technique not quite right? Yeah. Did the manufacturer supply us, did we misunderstand the spec of the tape? All of these challenges need to be dealt with.
And are these things you're actually just learning on the job, learning as you're understanding how to build these?
There's a lot of that. Yeah. And you're trying to build your knowledge base so that you've got as substantial a knowledge base as possible, and then you're doing rapid incremental innovation on top of that to
And
to
how does
up.
this approach this because you're building something that hasn't been built before. You're building something that's new. You're trying to create something that's never existed. How did this impact your hiring decisions?
Yeah, there are,
because it's not like you can say, well, we're looking for people with experience of building spherical
of radical innovation. No,
exactly. So did it impact your hiring, and if so, how?
Well, it did, because in the Oxford area, you have some mature superconducting magnet businesses. Oxford Instruments themselves have made high-performance scientific instruments from low-temperature superconductors for many decades. Siemens magnet technology, magnetic resonance imaging business, they make 40% of the world's MRI magnets in Oxfordshire. Now, the people working in those programs are working on not quite repeat and routine, but it is manufacturing discipline, not too much innovation, very structured approaches, and in MRI, obviously regulatory controlled challenges. So some engineers like that. The ones who don't are the sort of ones who joined our team to try new materials, to be in more of a skunk work sort of approach to seeing how far you can go with this new material.
Yes. And is there any advice you have for filtering out those skunk works lovers, those highly entrepreneurial Heath Robinson types?
Yeah. Well, they tend to cluster in particular parts of the world. They need. Oxfordshire is also great for motorsport engineering, Formula One teams, and that again is there's a certain culture of people who love. The petrol head love tinkering with the cars and trying to get them to go faster whilst remaining reliable. And we've got something of the similar ethos in the superconducting magnet area, that you need to design things. They have to be bold. They have to work.
They have to be precise. That love of precision and performance, and safety has to be in there too. But yeah.
And then, we then have challenges of scaling up of magnets. So the way in which you safely control a small magnet so that it can't burn out if there's a loss of superconductivity, a quench, it turns out to be very different, or requiring very different approaches and materials to go to a large magnet, where the stored energy in the system is much greater, and the risk of breaking your whole magnet system with a loss of superconductivity is a big challenge. So you have to be able to cope with that scale up challenge.
And David, bring this up to today. So the journey you've been on, you've just wonderfully articulated and summarized for us. Where is Tokamak Energy today? What does it want to be when it grows up?
We really, on the fusion side, we want to be at the heart of major projects aimed at delivering fusion energy. And we expect these projects to be backed by governments around the world. There's a great project called STEP in the UK, where we're in prime position to be the engineering partner, or part of the engineering partnership team to deliver that. We're engaged in the US milestone-driven fusion development program. And And we're in dialogue for a project in Japan, which would deliver, potentially fusion electricity in the 2030s, mid-2030s, if things go well. We're expecting Japanese government announcements on that fairly soon. And we know that in Europe, there's also growing enthusiasm for fusion, some very positive announcements in Germany.
Yes.
New government going very pro-fusion, which is interesting for Germany, given the challenges
its history,
they've had
with fission.
And then the European Commission also not wanting to be outdone by one of its member nations is looking at public-private partnership approach in fusion.
Mm-hmm. So it's about establishing itself kind of at the core of the entire value chain.
Yep.
And is this with the view of supplying services, engineering services? At some stage, does Tokamak Energy become a product company? Is it going to become hey, we now supply spherical tokamaks? Or do we partner up with Siemens and ABB and however many years, and they'll supply the tokamaks, but we provide the expertise and the support and, what exactly will it do? Or will it do all of those things, potentially?
Well, we shall see, but we were very fortunate a couple of years ago to get Warren East to join our board. Now, Warren was previously chief executive of Rolls-Royce, but prior to that, he was chief executive of Arm Holdings, which has successfully embedded its intellectual property in most of the world's advanced microprocessors.
Mm-hmm.
Now, when he joined, he said he wants to see Tokamak Energy become the arm of fusion, to own crucial intellectual property in all future fusion devices around the world. So if we can achieve that sort of high valuation, relatively low capital requirement to do the development, because we're partnering, but embedding our technology, software, know-how, systems, maybe high-value components as well within many devices. Fusion can take a few more years to develop. What won't change is humankind will continue to pursue fusion because it is so exciting and so important, and will inevitably be the dominant source of energy in the 22nd century. Just be good to get it sooner than that.
Do you think the world will allow it? Do you think,
yes,
given how fossil fuels are so embedded in and power the geopolitical landscape, energy powers the geopolitical landscape to a certain extent, and perhaps in the 22nd century, maybe when we've, but one of the questions or the things I worry about, if we were to create fusion, would the world allow us to use it?
Oh, I think so, because it's inherently safe. There's plentiful fuel. It doesn't require huge amounts of land.
Mm.
There are proliferation risks very, very low compared to fission.
Sure.
But I think what will drive fusion development is a bit of geopolitics. Particularly between the US and China. The US will not want to be left behind, and the new energy secretary has made that clear, that the US wants to be dominant in energy and in energy innovation. So we take that to be very positive. And of course, Europe won't want to get left out either. We're seeing that reaction quite strongly now.
Yes. But as China continues to dominate the market for many energy technology products, right now they have the leverage. and with
Yeah.
their form of government, which can get behind new platform technologies with
Yep.
all the might and capital required, and increasingly talents too. They're they may be the game to beat.
Yeah. Yeah. We watch with great interest what's going
Yeah.
on in China, and
Yeah.
it is not insignificant. And we have direct competition in spherical tokamaks in China, perhaps
Yes.
the strongest competition to our technology.
Interesting. The so Tokamak Energy is now at this kind of juncture. It's moved, it's along with continuing its development of the spherical tokamak. It continues to learn about and produce and design and patent new technologies and systems and materials, and work with partners to do all of this so that it can position itself at kind of the center of this emerging industry. When you think about the next phase of growth for the company and the skills it's going to need in order to fully occupy and its position in the value chain and play on a much more global stage, what skills and experience and talents will you need that you don't currently have right now, and do you think you'll be able to fulfill those from the UK?
Yeah, so there's different elements to this. I mean, one is our business model. For example, with the superconducting magnet side of the business, the model now is to look for large engineering companies that can basically take our technology and take it to very large markets, because they have the market relationship. So very recently, we've had a huge amount of interest from Japanese engineering companies. We have significant investment from Furukawa Electric, who own Superpower, so they're manufacturers of high-temperature superconducting material. They have assessed very carefully our engineering design capabilities and decided to make a substantial investment in the company, and then to introduce us to other large Japanese companies who are able to get superconducting technology into some very large opportunities. So that is one part of our strategy of leverage. So we will invest in the early stage innovation up to TRL 6 or 7. We can recruit enthusiastic magnet engineers who love the challenge of getting to that point. And then we hand over to either a joint venture manufacturing opportunity or a pure licensing or some other tech transfer arrangement, so that the product that depends on our technology is taken to market by someone else who has the go-to-market skills and the customer relationships.
Got it.
So we see that model, I mean, we have more than half a dozen large live opportunities of that type into quite different sectors. Propulsion systems for land, sea, air, space, where
Very interesting.
compact, relatively lightweight superconducting magnets can make a big difference.
Yes.
One of those projects is a DARPA project on submarine propulsion. It's in the public domain.
Yes.
Our magnets can deliver the magnetic field strength that is required for efficient magnetohydrodynamic drive, but the technology is going to be pretty complex to develop. So I don't think it's going to happen anytime very soon.
Yes.
But
in these
Yeah.
situations, though, then you are identifying additional applications,
Yes.
or additional application areas are being identified by someone,
Yes.
either
Yes.
from within Tokamak Energy or from someone outside who then looks at what you're developing and says, "Ooh, that's interesting." And
Yes.
so you have this, it's not quite the ARM model, because ARM focused on the design, or
Yeah.
here's a blueprint, and then the designers could then
Yeah.
go and design the chips using the ARM blueprint, and then TSMC would
Yeah.
make them. And but you've got, so you're designing some of it to a point, and you've got a whole library of patents and so on. And then in some areas, I'm guessing over time, you may go on to develop more of the technology, or
Yes.
advance it to a particular stage. In other cases, you may not need to do it as much, but you're then reliant on these relationships with these big global partners who can help you scale and get to market.
Yes. And then, of course, you have commercial negotiations. Is it
Yes.
non-exclusive license? Is it an
Yes.
exclusive license? What are the performance
Yes.
criteria?
Yes.
Is it
Yes.
split geographically? And
Yes.
so
David, if I were to
commercial
ask you
skills.
yes, yeah, no. So those commercial skills
Yep.
and strategic business development skills are critical there. Let me take you out of Tokamak Energy for a second. You've been in the industry for a long time. Certainly been very active in the science community for a very long time. If you were to look at the UK, and we talk a lot on this program, and it's talked a lot generally about the failure of our country of the UK to get more companies through the lab to market journey, through true TRL9 and in the market, and if they're manufacturing stuff, MRL10, and actually becoming proper businesses. If you think about that more broadly across the UK, is the model that you're developing, is that, could that become a blueprint for other companies, do you think? And do you think there are other things we could be doing as, within the UK to get more of these enterprises to market?
I certainly think there's more that could be done in the UK to get the sort of IP intensive early stage innovation companies to market. I think the UK is naturally good at the early stage innovation and tends to not be so good when it comes to large scale manufacturing. And I think trying to be good at large scale manufacturing, for example, of batteries, doesn't seem. I don't think we're likely to succeed in that. There are too many other countries who are better placed. But if it's more of a niche, like superconducting magnets, the UK is a world leader in high field superconducting magnets. With ourselves now and Oxford Instruments, Siemens, and others. That feels like a much more likely to succeed strategy than chasing
and reshoring
something.
and chasing a whole bunch of manufacturing.
Yeah. I mean, you need some of that, of course, but
of course, yeah.
But the ARM model, the high intellectual property model, the radical innovation, and then partnering, I think it's a nice way to go.
And perhaps the skill, because let's not forget the lessons learned from manufacturing and scaling are significant. They've enabled, I think, China to start developing their own IP, and and they enabled Japan and Korea and Taiwan and so on to become real innovators. So beyond just the manufacturing piece, all of that expertise they gained ultimately allowed them to become innovators too. And so it's but maybe to the point, by having those close partnerships with groups that are capable of delivering things at scale, and then taking the lessons, making sure that the executives or the talent in our businesses, is taking the lessons from their interactions and bringing some of that home so that we're able to capture that ourselves. Very often we see interesting platform technologies which may look good at the bench or in theory, but aren't ultimately scalable for one reason or another. And there's almost a sense that, well, had we been more of a mindset to think about the scaling challenges up front, we may not have gone down this line. And so a balance still has to be struck there.
Yes.
It sounds like.
Yeah.
Or closer relationships with manufacturers and OEMs. And
yeah, I mean, one of the things that has surprised us over the last couple of years is the number of new applications of the high temperature superconductors that we've become aware of. And that's often through dialogue with supply chain and then sort of coming across people finding out you have a potential solution to somebody's problem. So the most recent of those is the possibility of using superconductors in data centers. So data centers are increasingly power hungry. The power density of the data centers is going to increase dramatically with the latest NVIDIA chips. So that they're going to go up towards 1 megawatt per rack from 130 kilowatts or whatever it is at the moment.
Oh, wow!
So this is astonishing power requirements, and to get the power to the chip, you need bus bars. At the moment, they use copper and aluminium, and these bus bars are getting big. So they're occupying a significant amount of space within the data center, and they're generating huge amounts of heat. So on the other hand, they're conventional and routine, easy technologies. But the point is going to come where it's worth having a high temperature superconducting busbar in these data centers, because it will deliver 5 times the amount of power in the same footprint as copper. And even more so for
That's
aluminum.
fascinating. Are you guys scouting out these applications, or is the demand side approaching you? Or is it a mix of both?
It's a mix. Yeah, it's a mix. It's things we've become aware of. And then you start to investigate in more detail, and then you find there's a debate in the industry. Are we going to go to superconductors in the next generation, or is it 5 or 10 years down the track? And then you get some of the... So, I mean, we couldn't go to market directly with a technology like that. We'd have to partner with an engineering player who's already supplying into that industry. So some of those are very cautious and very slow moving. Others are open to innovations that might come through the market in 2 or 3 years. So
okay. David, one final question for you. When do you think we're going to have nuclear fusion reactors actually producing nuclear fusion?
Well, our ST40 does nuclear fusion, every day, or most days. But it takes a lot more energy into it than it outputs. If you're looking at electricity generation, then I think 2034, 2035 for electricity generation at meaningful scale. And I'd point to the US milestone-driven fusion development program and possibly a new Japanese program that might aim realistically at that time frame.
So within 10 years?
Yep.
Great. Well,
electricity
that's exciting.
from fusion. Yep.
That's very exciting. David, I've loved having you. Thank you so much for joining me today. It's been great. I'm sure our listeners are going to love it.
Thank you, Chris. I enjoyed it as well. Thank you very much for the questions. There's some challenging questions in there. Excellent.
You've been listening to the Lab to Market Leadership Podcast, brought to you by Deep Tech Leaders. This podcast has been produced by Bauhaus. You can find out more about us on LinkedIn, Spotify, Apple, or wherever you get your podcasts.